Bismuth strontium calcium copper oxide, or Bscco, pronounced Bscco, is a family of high-temperature superconductors having the generalized chemical formula Bi2Sr2Cn-1CuNO2n plus 4 plus X, with N equals 2 being the most commonly studied compound, though N equals 1 and N equals 3 have also received significant attention. Discovered as a general class in 1988, Bscco was the first high-temperature superconductor which did not contain a rare earth element. It is a cuprate superconductor, an important category of high-temperature superconductors sharing a two-dimensional layered, perovskite, structure, see figure at right, with superconductivity taking place in a copper oxide plane. Bscco and Ybco are the most studied cuprate superconductors. Specific types of Bscco are usually referred to using the sequence of the numbers of the metallic ions. Thus by 2201 is the N equals 1 compound, Bi2Sr2Cu06 plus X, by 2212 is the N equals 2 compound, Bi2Sr2CaCu208 plus X, and by 2223 is the N equals 3 compound, Bi2Sr2Ca2Cu3010 plus X. The Bscco family is analogous to a thallium family of high-temperature superconductors referred to as Tbcco and having the general formula Tl2Ba2Crn-1CuNO2n plus 4 plus X, and a mercury family Hbcco of formula Hgba2Crn-1CuNO2n plus 2 plus X. There are a number of other variants of these superconducting families. In general, their critical temperature at which they become superconducting rises for the first few members and then falls. Thus by 2201 has Tc33K, by 2212 has Tc96K, by 2223 has Tc108K, and by 2234 has Tc104K. This last member is very difficult to synthesize. Bscco was the first HTS material to be used for making practical superconducting wires. All HTS have an extremely short coherence length, of the order of 1/6 nm. This means that the grains in a polycrystalline wire must be in extremely good contact, they must be atomically smooth. Further, because the superconductivity resides substantially only in the copper-oxygen planes, the grains must be crystallographically aligned. Bscco is therefore a good candidate because its grains can be aligned either by melt processing or by mechanical deformation. The double bismuth oxide layer is only weakly bonded by van der Waals forces. So like graphite or mica, deformation causes slip on these BIO planes, and grains tend to deform into aligned plates. Further, because Bscco has N equals 1, 2 and 3 members, these naturally tend to accommodate low-angle grain boundaries, so that indeed they remain atomically smooth. Thus first-generation HTS wires, referred to as 1G, have been manufactured for many years now by companies such as American Superconductor Corporation, AMSC, in the USA and Sumitomo in Japan, though AMSC has now abandoned Bscco wire in favor of 2G wire based on Ybco. Typically, precursor powders are packed into a silver tube, which is then extruded down in diameter. These are then repacked as multiple tubes in a silver tube and again extruded down in diameter, then drawn down further in size and rolled into a flat tape. The last step ensures grain alignment. The tapes are then reacted at high temperature to form dense, crystallographically aligned by 2223 multifilamentary conducting tapes suitable for winding cables or coils for transformers, magnets, motors and generators. Typical tapes of 4 in width and 0.2 thickness support a current of 200A at 77K, giving a critical current density in the by 2223 filaments of 5 × 105A/cm2. This rises markedly with decreasing temperature so that many applications are implemented at 30 to 35K, even though TC is 108K. For making superconducting chips, it was suggested that due to advances in blue laser technology, notably 445, 450 and 405 nanometers single-mode diodes, it may be possible to selectively nudge the SR atoms in by 2223 to preferentially form HIGH, TC materials designed for computer chips. If so, then the setup for making these in bulk may be very simple, such as a MOT insulator pellet surface modified with Bscco via MOVCD and then laser annealed under oxygen at a very specific set of electrostatic fields, temperatures and wavelengths sequentially, with the polarization aligned to the grain boundaries. If the 2223 variant is used, then TC may substantially increase and thus make the material suitable for a quantum sensor, SQUID and other applications needing these parameters. This idea was suggested on Twitter and a paper is being compiled with further information for release around 3Q2018 and further discussions on 4HV.org. The original idea was inspired by the single glowing strontium atom sitting between electrostatic plates in a vacuum, which incidentally won the PhD student responsible an award.